Welcome to our tutorial series about transformer protection. In our transformer protection webinar series, you can gain a comprehensive knowledge about the most important protection functions, typical transformer protection applications, and you can learn how to configure a 7UT8 in DIXI 5 and test it with our CPROTEC 5 digital twin. In this session, we will talk about the challenges that exist when it comes to testing a transformer differential protection relay. We also present the possibility of simulation-based testing with the software Relay SimTest from Omicron. This also works in a completely virtual environment together with our CPROTEC digital twin solution. If you already joined one of our last electrification and automation webinars, you already know the Q&A field on the upper right side in this application. Please enter your questions there. My name is Nina Hühn and I am technical expert for differential protection, and I have a guest today. With me in the studio is Lukas Smoot. He works for Omicron, among other things, as a trainer for secondary testing, and he can demonstrate to you firsthand the benefits of Relay SimTest. Welcome, Lukas. Now, let us start with my small theory part and then I will hand over to Lukas. Here you see the agenda for this session. In my presentation, I will start with the results of a customer survey we made, followed by the key challenges for transformer differential protection. Then I want to explain new features introduced in CPROTEC 5 compared to previous CPROTEC 4 protection family. Next, I will show you the example configuration Lukas will use for his demo part. I will finish my part of today's session with presenting the general benefits of a virtual testing approach using the CPROTEC 5 digital twin. Then I hand over to Lukas and he shows you the benefits of Relay SimTest and gives you a demo. Alright, let's get started with the customer survey. On this slide, you see the results for little customer survey popping up. These are the protection functions and network conditions that our customers want to test. This includes, of course, in quotes, the classic protection tags like tripping times, the differential protection characteristic, and the threshold values of the different stages that we have. But our customers want to validate the blocking conditions as well for inrush currents using both the traditional second harmonic method and the new CWA technique and the blocking conditions for overexcitation. The test should also generally confirm that the protection relay is stable in the event of external fault and trips reliably in the event of internal fault, and that it behaves selectively under the given network conditions. The next question we asked the customer was, which test cases cause you the most problems? Here, on the one hand, points were mentioned that result from measurement processing done in the relay, such as vector groups, side currents, matching factors, tap changer adaptation, and so on, which can get complicated, I admit. Again, on the other hand, the blocking functionalities that we offer were mentioned as challenging when it comes to testing. One topic which is always coming up since the function was released is the question of how to test the CWA blocking versus the CWA internal fault detection. Among other things, this function means that it is often no longer sufficient to test under steady-state conditions. Okay, so we know transformer differential protection and therefore the testing of transformer differential protection is not always easy. Why? What are the challenges for transformer protection relay? The key challenge is the need to accurately differentiate between various conditions. For example, a transformer inrush, an overexcitation state, as well as internal versus external fault conditions. This task has become increasingly complex due to the growing number of inverter-based generation, which can introduce significant second, third, and fifth harmonic content into the system. These harmonics can significantly impact the stabilization methods used for inrush detection and blocking. However, dynamic algorithms lead to considerable problems in conventional secondary testing. With conventional secondary testing, I mean that you use, for example, Omicron QuickCMC or the state sequencer, where you define pre-fault conditions and fault conditions on your own and independent of the given network topology. Of course, you can still use this procedure to test the threshold values or operation times. However, if you want to find out whether the 7UT is behaving correctly under the given grid conditions, for example, in the event of a transformer inrush, you need a different approach. Omicron Relay SymTest offers one possible solution for this, but Lucas will tell you more about this later. For now, I would like to take a step back and talk about our algorithms, about new features and improvements implemented in the last years. One of those features, what is worth mentioning here, is our CWA method as improved inrush blocking method. So the customer requirement is that the protection relay is stable at inrush currents when switching on a transformer, which should be also stable in case of a sympathetic inrush when switching on a parallel transformer. Siemens offers two inrush detection functions with two different measuring principles. The first one is the second harmonic evaluation. Second one is the CWA method. CWA is short for current waveform analysis, and as its name already explains, the CWA method analyzes the current waveform, detecting flat areas. On the right side of the slide, you see a typical current waveform during an inrush. Marked with a red cycle is one of those flat areas what I'm talking about. The CWA function and the second harmonic detection work in parallel, and the blocking is a 1 out of 2 decision. If either the second harmonics are above a settable threshold or the CWA method detects the characteristic flat areas, the differential protection is blocked. If the CWA method does not find any flat areas precisely one period after fault inception, an internal fault is assumed. The main benefit is an increased system availability due to the increased stability at inrush currents. The next change I want to mention here is the improved restraint algorithm. Compared to CPROTEC 4, we changed the way of calculating the restraint current. Again, what is the customer requirement? The customer requirement is, on the one hand, to have a high sensitivity to low fault currents and to be sensitive also when it comes to circuit breaker and a half applications, but on the other hand, to have a high stability against external faults. Our solution is to work with the conventional, well-proven restraint characteristic, but new is the calculation of the restraint current. In CPROTEC 4, the restraint current was the sum of all side currents. Now we use always the biggest of all side currents, but only one current, not all of them. Therefore, the settings of the characteristic needs to be adapted, and this must be considered when testing the function. The benefits are an increased system availability, a higher sensitivity especially for circuit breaker and a half applications, and more stability at signal distortion. The last improvement I want to mention today is the change we made in the IDIF fast stage. The motivation is to achieve with this stage short tripping times at high internal fault currents, even when CT saturation occurs. In contrary, we need stable behavior at external faults, even for circuit breaker and a half applications. To achieve that, the 87T fast stage evaluates the instantaneous values of the differential current. Here, the very first few current samples in the saturation-free time of the CT are used. What we implemented for the transformer differential protection is the same method as we have for our well-proven busbar protection. The trip decision, if it is an internal or an external fault, is based on a characteristic. So there is a threshold and a slope setting. This is different compared to CPROTEC 4. In the past, we had only a threshold value for the IDIF fast stage. The main benefit is an increased system availability due to the improved stability at heavy external faults. So when testing the AT70 function, actually two characteristics need to be considered in the test setup. If you want to use, for example, the Test Universe Advanced Differential Module, you must set a differential characteristic 2 times, and both characteristics need to be tested independently from each other. Okay, so much about the theoretical part of today's session. For the demo part, Lukas and I prepared a relay configuration together. The device that will be simulated in the CPROTEC 5 digital twin is a 7UT86. We decided to work with the templates or examples that we offer in DIXI 5 and in the Relay Sim Test library to make things easier for us and more importantly for you when you want to do some tests on your own. The relay configuration was created in DIXI 9.90 and we used the application templates Rewinding Transformer Basic as starting point. In addition to the functions the template already offers, we inserted a function group transformer neutral point and the function restricted earth fault protection. The names and CT ratios were adapted according to the example that Omicron offers for their software relay sim test. Okay, now give me 2 more minutes to promote our digital twin solution before I hand over to Lukas. Our CPROTEC Digital Twin Cloud solution is available anytime and everywhere. It can be used before updating installed devices, before starting commissioning, before building up panels, and even before purchasing devices. The benefits of our digital twin are a hardware-free testing solution for validation of product properties. It can help to achieve faster energization times because you can start with your virtual tests before the start of commissioning. This can lead to shorter commissioning times and an increased engineering quality. With the digital twin, you can reduce the OPEX costs with shorter outages for higher availability thanks to the better pre-testing. The digital twin is great for training purposes and for fast and realistic fault analysis after network fault has happened. Okay, that was my last slide. Now I would like to hand over to Lukas. Lukas, welcome on stage.
Before we dive into the functionality of Relay Sim Test, we'd like to have a little insight into the setting-based protection approach. This is performed with Test Universe. The test is performed for parameters like distance zones, thresholds, and differential tripping characteristics. There is a comparison with predefined values to assess the result. This is a tried and tested method. But we did not test for the communication between relay and other relays or other devices in the network. Also, we did not test the logic and interaction with other protection functions. Finally, we did not test the concept of the protection function in regards to the attributes of the object to be protected. Testing with Relay Sim Test depicts the test using a system-based approach. The first step is to recreate a section of the power grid. Of course, our device to be protected, like a line or a transformer and adjacent components. By using a transient power system simulation, we verify that the relay distinguishes between load and fault scenarios. Therefore, we can identify errors in not only the setting of the relay, but also in the logic in the relay and the communication and interaction with other devices. The maximum of testing depth can be achieved by using both variants, the parameter and system-based testing approach. Studies have shown that more than a quarter of malfunctions in the protection scheme are due to errors in parameters and design. This can be an incorrect set parameter or an insufficiently chosen protection function. The main key features of RealSim test consist of the usage of transient signals to maximize the realistic behavior during events. Transient signal is needed to simulate various behaviors during faults or after switching events. At first, a CT saturation can be remodeled, as the iron core of the CT is saturated. A fraction of the sinusoidal current will not be transmitted on the secondary winding. Protection relays will detect a saturation and can be tested for stability. The inrush current that appears during switching on a transformer can also be simulated. A power swing in which current and voltage rise and drop continuously can be modeled. During that state, the relay is tested for stability. No trip should occur. An intermittent ground fault can be simulated by just activating one checkbox. Also, the control of many test sets with one computer is one more key feature of RealSim test. Of course, it is preferable to have only one test report, even if using multiple CMCs. Still, the test is more comfortable if performed from one side. That's because all changes will be made with just one computer that controls all outputs. Of course, one basic target of controlling multiple CMCs is the end-to-end testing of line protection schemes, like line differential and teleprotection. But it is also useful when used, for example, during busbar protection. The easiest way to gain control of another test device is by using a not used communication channel, either Ethernet or fiber optic. Another possibility is to use an internet connection using a cloud that allows another computer to be controlled remotely. Finally, the classic method to use a fixed time trigger is still available. Let's finally have a look at RealSim test itself. When you want to test with RealSim test, you may start with a new test document. Unlike Test Universe, you will not start from a complete blank document. You may either start from a line topology or from a substation topology, or you can choose from our Omicron template. There are many possibilities for many different relays, and of course today we want to have a look at the transformer protection relay. Here we have, for example, the 2-winding transformer differential protection template or the 3-winding transformer protection template. Still, there are many other protection templates, like for phase shifting transformers or for auto transformers. But right now, I'd like to keep the basic RealSim test functionalities. So in this case, I'd like to start from the line topology. The heart of RealSim test can be found in the power system. That's where you need to remodel your power system to be tested. As you can see in the line topology, there are many components already pre-configured, like an in-feed, a current transformer, a voltage transformer, the line itself, and circuit breakers on both ends. As you can also see, there are 2 relays already connected. As soon as you click on the relay, you will see the connection that is already made to the circuit breaker and the interaction with the current transformer and the voltage transformer. By clicking on each device, you can set its features, like the CT ratios that can be changed. You can even model it as a dynamic behavior to simulate saturation. Of course, you have to then edit your CT data. The line parameters can be set in various manners. You can set it as a total R and X values, or you can set it as values based on the length. Furthermore, you can set it as an impedance in relation with the k-factor. To increase the realistic behavior on a line, you can activate the mutual coupling with another power line, or you can enable a capacitance. On the top bar, you see so many components that you can enter. To enter it, you can simply choose your component that you want to enter, like maybe another line, and click on the white panel. After that, you can simply drag and drop and connect it to another device. This way, you can set up your grid like you need to for testing. As soon as you're done setting up your power network, you can perform the test set configuration. That means you can route the current and voltage to be output by your testing device, the CMC. In this template, you can already see that the connection was already made. This CMC will output the voltages from voltage transformer A and the currents from current transformer A. Furthermore, you need to define your binary inputs coming from the relay. In this template, we have the trip command and the close command for the circuit breaker A. When you're done with this step, you can enter your simulation test and perform the real test. For example, you can enter faults and verify if the relay is working correctly. Before I go into this step, I like to explain the usage of the digital twin. To start the connection with the digital twin, you need to enter another device, and that's called the digital twin connection. As soon as you enter it, your test sets disappear because we no longer need a CMC to perform the test because it's all performed virtually. So for right now, we want to have a look at a detailed test of a 3-winding transformer. To do so, let's open this prepared test file. This relies heavily on the template that can be found when creating a new test. So we have a 3-winding transformer. You can have a look at the infeeds and you can verify the parameters. Most important one being the nominal voltage of each infeed. So we have 3 infeeds consisting of a 220 kV, 110 kV, and a 10 kV infeed. Furthermore, let's have a look at the transformer parameters, like the rated transformer voltages, the rated powers for each side, and then you can edit a lot more functions like short circuit voltages, short circuit resistances, and of course the dynamic behavior, because we want to verify that this transformer works precisely when being in saturation. Finally, let's have a look at some tests. Of course, we want to prepare a digital twin connection and have a look how that's done. I'm going one step ahead because as soon as I open a test case and I click on select, there's actually a little guideline on how we can set up the connection with digital twin. So at first, we have to go to the web page and log in. Then we have to export the SIM file from the DIXI5 parameterization software upload it to the digital twin software, and prepare the devices. Then we have to at first export the state sequencer XML file. This is responsible for the connection and interaction between RealSymTest and digital twin. So let's do these first 3 steps at first. Let's create a state sequencer XML file because that's responsible for the connection to the digital twin. So I'm already connected with the digital twin, and as you can see, there is already the relay imported. You can import in the pane test files your API reference file. After that, like in the real world, you have to do the routing, or let's say wiring, but today this is in a digital manner. At first, we, let's say, wire or route the currents. So the source from our currents or outputs in general, of course, can be voltages, is our API reference file. In other words, RealSymTest. Of course, our relay is routed, or let's say the project is routed for different current inputs. And of course, you have to route them just like you would connect currents in the real world. After that, you have to wire your binary traces. And in this case, the binary traces are routed from the relay to our API reference file. That's because we want to receive binary traces and be able to test them. In the same manner, you have to connect them like in the real world. Let's then have a look at the next step. The next step says we have to select the device and start the simulation to power the devices up. After making sure that we have the correct cProtect Digital Twin license, we can continue with the next step. That is copying and pasting the API password. This can be found again on the Digital Twin homepage in this menu. We open the API password, copy the password to the clipboard, and paste it in RealSymTest. In this case, this password is the same as before from my previous connection. So far for the connection between RealSymTest and Digital Twin. Let's finally have a look at testing and have a look at the various test cases. I have reduced the number of test cases to my most important ones, and I've grouped them into 2 different groups. That means at first I want to test for stability. That means I have several cases in which there should be no trip occurring. That is, of course, for regular load flow on tap 0. Tap 0 means I also have included a tap changer. This tap changer has currently only 3 taps of course, you can vary that, and you can vary the voltage to keep the voltage on the secondary side constant. Of course, when switching the tap changer, the transformer relay should also not be tripping. Therefore, I have the second state when I change the tap changer to my second position, when no trip should be occurring. Also, when applying a different tap minus, and also with a little CT error, which is available in a realistic behavior, the relay should also not be tripping. During external fault, that means a fault outside our protected area. Remember, our protected area is limited by the placement of our current transformers. That means the differential protection function only evaluates currents in between the current transformers. Any faults outside of that should not lead to tripping. Finally, I have cases for inrush currents when switching on a transformer and for overexcitation when the voltage rises. After testing for stability, we want to test the relay to trip precisely. I have several fault types. For example, a turn-to-ground fault on side A of the transformer, a turn-to-turn fault on side A of the transformer, an evolving fault, an inrush with fault, and we have a final test case, REF faults, when only the REF, the restricted earth fault protection, will trip. Let's have a look at some of our test cases. Let's start with the load flow. In this test case, we have 4 test steps in which we vary the phase in between our 2 infeeds. As you can see on our current simulation, the current rises depending on the angle of the infeeds. Of course, in all 4 test steps, the relay should be stable and not be tripping. Let's execute them all, see what happens. As expected previously, the relay did not trip on any of the 3 sides. This can be defined with the define measurements pane. In this area, we define our signals to be measured. So a general trip is measured from our measuring event, that is the start of the simulation, until the occurrence of the trip signal on the relay. But remember, this is a stable case. We did not expect the relay to trip. So we choose the according assessment condition, that is, the start event should occur, but no stop event. Remember, this was the trip signal, the stop event, defined previously in defined measurements. So the minimum time to be expected is now plus infinity. That means we don't expect a trip signal. So therefore we didn't, and the test passed. Let's have a look at some other test cases, for example, the load flow with another tap. So as we vary the secondary current by choosing a different tap on the tap changer, the actual rated current differs a little bit from our fundamental parameterization. That means there is actually a little differential current to be expected, but this differential current should not be high enough to trip the relay. As you see, the relay did not trip. Next, we have a load flow test case with a CT error. You can see this in traces of the analog outputs. That means this case CTA has got a ratio error on phase number 1 of plus 10%, and CTB has got an error of minus 10%, also on phase L1. You can see in the analog output traces the red phase of L1 is a little higher than the other two, and in output B, phase L1 is a little lower than the other two. Still, this should not be high enough to trip the relay. Let's finally have a look at various faults outside our protected area. That means a fault on the bus bar should not be detected by our differential relay. Again, no trip should occur. Perfect. As mentioned previously, we'd like to have a look at the stability during an inrush. So, the event right now is the switching on process of circuit breaker A. As the transformer is modeled in a realistic behavior, so we activate the transformer saturation, and therefore, even though all other circuit breakers are switched off, no trip should occur. Even if there is actually a differential current, you see there is only current on CTA, not on all other CTs. Depending on the detection method, the relay should not trip, and this is because both of the appearance of the second harmonic and the CWA detection. So, we see there was no trip and no output of the relay. But in this case, we defined another measurement, that is the appearance of the inrush detection. This was also parameterized as an output on the relay, and we made a connection to digital twin. So actually, we had an inrush detection that was responsible for the blocking of the relay. Finally, let's continue with some trip time tests. To do so, we have to insert at first a fault. After you choose, you see on the blue highlighted areas the possibilities of inserting a fault, and right now you see that there was already a fault placed inside the transformer, and we will test for that. So by clicking also on the fault, you can change the fault types, and as indicated by the name of this test case, we will test for a turn to ground fault. We vary the parameter, we change the location of the turn to ground fault, but we keep the fault resistance constantly. Depending on the fault location, the relay tripped in a different trip time. But the most important thing is it tripped. Another fault type, in contrast to fault to ground, is the turn-to-turn fault, when there's a short circuit between turns inside the transformer winding. Still place them on the primary side. Of course, you can change in further test cases the test to secondary or even tertiary side and test for the correct tripping. So in the first 3 test steps, the relay tripped as expected. In the final one, there was a special test step because the fault was placed in between 99% and 100% of the winding. That's alright for the relay not to trip because the fault was really close inside the windings, but we kept the assessment accordingly to allow the relay not to trip. That's alright. The next test case focuses on evolving faults. That means at first we have a fault outside our protected area on the bus bar A. After that we will have a fault inside the transformer. And of course, after the appearance of that fault, the transformer relay should trip. An evolving fault appears when there is an increased voltage outside the transformer that leads to a final short circuit inside the transformer. Let's have a look at the test. Again, the relay tripped in all 4 test cases as expected. Of course, you can combine multiple events. For example, let's combine the inrush with a fault. The order of the events to appear is, at first, we will switch on the transformer. We will switch on the circuit breaker before that. That leads to an inrush. But after only a few milliseconds, there is a fault. And of course, the blocking should be deactivated and it should lead to tripping. And again, it tripped as expected. Let's have a look at the final test case where we apply faults, and some of them may only be detected by the restricted earth fault protection. As you can see, there is another current transformer inside the star point of the transformer. Together with the 3-phase current transformer set out on the same winding, we can apply the REF protection function. Here we have placed various transformer turn-to-ground faults on winding B. Some of them only have very little differential currents and will only be detected by the REF protection function. So if you have a look at the outputs of current transformer A and B, you will see that they only very little, or maybe it's quite hard to see that there's actually a fault here. But you will see that the REF protection function will detect all of them. Actually, the second and the third test step, the transformer differential relay did not detect the fault. Instead, the REF protection function did detect the fault due to the increased sensitivity. Still, of course, depending on the fault location in regards to the distance to the star point. The transformer differential protection will detect the fault together with the REF protection function, or also depending on the fault resistance, because this one is increased in regards to the previous test steps. Only the REF protection function detects this fault. Okay, so I showed you how to set up a test for a differential protection relay using Siemens Digital Twin and Omicron Relay Sim Test in only a few steps, without actually having a relay and having a real CMC test set. Thank you for listening.
Yeah, thank you very much, Lucas, for this very interesting demo of how to test a transformer differential protection. And of course, thank you for listening for our last 5 sessions, sorry. Now beside me is Sebastian, and we have time for your questions. Over the last 4 sessions, we received a lot of them. Thank you also for that. It's very good to see that you are interested in the topic and curious. So we brought some of the questions with us today and we'll answer them. And if we have the time, of course, we will take a look at also of the questions that were like from today live. And if we cannot manage to answer all the questions today, of course, you can be assured that they will be answered in a written format and you receive them afterwards. Okay, the questions I brought with me, I clustered them a little bit and I read them now to Sebastian and I have only the moderator part. So the first topic I want to talk about is the ZIPOTEK 4 to ZIPOTEK 5 migration path. So here the first question is, does the transition from ZIPOTEK 4 to ZIPOTEK 5 require changes in cabinet wiring also, or is it only a hardware change of the device?
Yeah, thank you for the first question, Nina. Yeah, I would say it's not a change of a wiring necessary. So finally, it's just a hardware change. So of course, for differential protection, 2-winding transformer, for example, you just need 8 times current, yeah, and of course you need the trip circuits and so on. So that means it's just a replacement by the hardware.
Okay, well, maybe just it's not written here, but would you say are the CT requirements comparable, ZIPOTEK 4 to ZIPOTEK 5?
Of course. Of course, it's comparable due to the fact that we are also using a new algorithm for the stabilization method, and also the accuracy and the resolution of ZIPOTEK 5. We could reduce the CT requirements. So that means for retrofit applications, you can find. Beside that, what I say, you can find, of course, in the manual, our CT recommendations in the appendix A8, and you will see there. So that means ZIPOTEK 5 is also, matching the same CT requirements. So,
Okay. Next question is, how can we migrate the setting from ZIPOTEK 4 to ZIPOTEK 5?
Yeah, you can migrate the settings via the migration tool in ZIPOTEK Digital Twin, for example, but you have to be aware of the new stabilization method. What we are using now, we are using just only one of the we're using all the measuring points, but the measuring point which gives the highest restraint current is used. So that means it's adaptable. So therefore the characteristic is a bit changed. So therefore you have to pay attention on the characteristic and on the intersection. So finally also the intersections is now defined different to ZIPOTEK 4. But anyway, you can take all the settings, or you can take over all the other settings. one difference between CPROTEC 4 and CPROTEC 5 is also that we have now the ID fast stage, which is also stabilized now. So, and the recommendation for this ID fast stage is to consider the highest inrush current of the transformer.
Okay. Would you say if, for example, someone has a CPROTEC 4 device and he was very happy with the default settings of the characteristic, and now he buys a CPROTEC 5 device, I guess he can also stick with the CPROTEC 5 default settings and can expect the same functionality,
he
right?
He will lose with CPROTEC 5 now then the advantage that the adaptive settings for CPROTEC 5 7UT, he will lose a bit the sensitivity. So because the CPROTEC 5 system is much more sensitive in terms to CPROTEC 4.
Okay, yeah, understand.
Or comparing to CPROTEC 4.
Yeah, so we are, of course, getting better, not worse. Okay, next topic I called special applications. So here the first question is about shunt reactors. Is the shunt reactor treated as a transformer in our CPROTEC 5 configuration?
At the moment, yes. And at the moment, you can use a two-winding transformer for shunt reactor applications, but we are currently planning to have our own function group for shunt reactor application, which includes then in the end also a special turn-to-turn for protection for shunt reactor. So therefore, with the next release, or version 11 dot, I don't know, we release a shunt reactor application specially. And of course, you can use transformer protection instead. But with the next release, as I said, we have a special function group then for shunt reactor.
Great, yes. And I would say at the moment, of course, you use the 87T as like main protection function, but for backup, we recommend the 76N, right?
Yeah, right.
And of course, also the restricted ground fault protection can add some sensitivity for the protection scheme of a shunt reactor.
Right. It's always a question of a combination of different functions. So that means in the end, we can detect different kind of failures in a shunt reactor. So usually the differential protection is covering all the failures face to ground, face to face. The restricted fault is a bit more sensitive, is detecting face to ground failure, which is close to the neutral point. And the 67NS directional element based on the negative sequence is covering all the winding faults. And as I said, with version 11.x, we will bring a new function group, which contains then an incremental turn-to-turn fault protection for shunt reactor.
Okay, great. Next question would be, can it, so the transformer protection device, of course, it be used in application where there's an VSD transformer?
VSD stands for variable speed drive transformers, of course. The 87 or the transformer protection is based on the frequency tracking. So that means we can track the frequency from 10 until 90 hertz. So then, and with this capability of the frequency tracking, we are able to protect variable speed drives. That means where the system frequency is not according to 50 hertz. So it can be, for example, for hydropower stations, sometimes 30 hertz, for example. And this is possible,
okay. And last question under the topic special application is, can we use the 7UT for busbar differential protection?
Good question. This question comes very often, to be honest. Clear. It can be used for busbar differential protection for single bus bars. Of course, the 7SS85 is recommended for busbar protection, but here you can use as well the 87 for small busbar up to 5 feeders. You can use it, and then you have to program it as a virtual transformer with the ratio 1:1 and a Y0 transformer, for example, and then you can use it also as busbar protection.
Maybe just a small hint, also since version 9.90, I think, in the 7SX, we now also have a dedicated busbar differential protection function. Okay, so next topic I called auto transformer. So here, first question is, can the 87TS accommodate effectively an autotransformer without the presence of closed delta winding?
Yes. We can use the 87T, we call it node. So that means the part of the autotransformer which is galvanic coupled with each other. So that means we can use that one as a node point protection. And when we don't have the CDs on the delta winding, usually the delta winding is used for auxiliary power supply, which have also a very low power on that side. So we can consider that in the characteristic, not to set it so sensitive, but this is possible. The advantage of our 87T protection for autotransformer is that you can usually have two kind of protection or differential protection as in one device, which is working parallel. One is the node point protection for the galvanic part, and then we have the normal power transformer protection for the part with the delta winding.
Okay. Yeah. Here, maybe an outlook to the future. If you are interested in this topic, autotransformer, we have a second webinar series about transformer protection. Mainly presented by our colleague Klaus Wagner, and he will have a dedicated session about autotransformers. So, if you want to get deeper in the topic, stay tuned. Next question is for the 87N dedicated to the autotransformer. Why does function stay with the 87T, while for power transformer it stays on two different function groups?
Okay, good question. Good question. The 87N, the restricted earth-fault protection, have two different kind of implementations. For a power transformer, we have to compare the neutral point current on the neutral point and compare it with the 3I0 from the transformer side. That's the reason why the 87T is for normal power transformer instantiated in a transformer side. For an auto transformer, we need to consider both sides. That means both auto sides. That means we have a 3I0 from side 1, the 3I0 from side 2, and we compare these with the neutral point. So that's the reason why the implementation is a bit different for auto transformer. And that's the reason why you have to instantiate the 87N for autotransformer in the function group autotransformer diff. But I think this will be more explained in deep when Klaus Wagner is giving the session.
I'm sure he will also give some hints about how to configure this function, yes. Okay, so much about the autotransformer. Now the next topic is about inrush current detection. First question, will the inrush current detection add additional processing time in the tripping signal? In the trip signal.
Yes, clear, because for the second harmonic and also for CWA, for the restraint characteristic, of course, we need one period to do the Fourier analysis. So therefore, with the restricted characteristic, that means with the sensitive characteristic, we need to add 20 milliseconds, up to 20 milliseconds to do the analysis, and then we can say, okay, this is an inrush, or this is an internal or an external fault. So therefore, usually all the other manufacturers have the same implementation. This is based on the mathematics, of course, and we need to have the first period to make the discrimination between internal, external, or inrush.
But as you already said a little bit, for the very high fault currents, we still have the fast stages. So if there is a high fault, it will be tripped.
Of course, that's the difference. The restraint characteristic or the restraint characteristics is working with the fundamental wave, and the high set stage, like the either fast and either unrestrained stage, is working with instantaneous values. And due to that fact, of course, you will have different tripping times. And if you compare these with the technical data in our manual, you will see the tripping times are different. So that means for the fast stage, we have up to 8 milliseconds tripping time, and usually for for the restraint stage, we have tripping times around 28 milliseconds.
Mm-hmm. Understand. And maybe the last question of this block is really fitting to this discussion. Does the IDIF fast stage not get blocked by second harmonic detection?
Right. The IDIF fast stage is not blocked by second harmonic and not blocked by CWA, of course, because this IDIF fast stage, the rule for setting the IDIF fast stage is to set the stage over the maximum expected inrush current. For example, for a 40 MVA transformer, you have to set the fast stage over 5.5 nominal current of the protected object. And this is a value which you can see in our manual. There's a setting recommendation, and you find a nice little diagram to figure out what is the related inrush current for my transformer.
Okay, yeah. Okay, next question. If fault occurs during switch on, when differential function is blocked due to second harmonic restraint, will relay trip during this time, or will relay wait for the second harmonic timer to finish and then trip?
That's really a good question. So we discussed these several times. Beside the CWA for inrush detection, we have the CWA for internal fault detection. That means if I have a switch on to fault, usually the sinusoidal is there. So that means we have no flat areas in the sinusoidal. And this is used for detecting internal faults. And with the CWA internal fault detection, we suppress the second harmonic. That means immediately with switch on to fault, we check, okay, we got the condition, it is an internal fault, and then we suppress the second harmonic. That means the blocking is then dropped out in that case, and we do not have to wait until the blocking is gone. Especially the same implementation we have as well for evolving faults, for example, or for faults with a high second harmonic due to CT saturation. And that was the initial, or that was the motivation why we are using a different criteria or a different detection for this internal fault detection, to say, okay, we are independent from the second harmonic because we had already this failure in the network where we have internal faults with very high CT saturation, and due to the CT saturation, you got a high amount of second harmonic. And in those cases, we had a bad combination with the settings. Of course, the customer was setting the threshold for second harmonic to 8% to 10%, for example, and with a very long time. In one case, we had one case where the customer was setting the cross block to infinity. So that means the differential protection has no chance to trip due to the fact that the second harmonic was blocking all the time. And with the CWA internal fault detection, we are able to unblock the blocking, or to drop out the blocking, and to trip immediately.
Interesting. So very detailed question here also. Great. And next topic I called under the headline CT requirements. You had a dedicated session about that. So here the first question is, where does this requirement of 80% remanence come from?
I think that the topic with the 80% of remanence is coming from the standard so far, because closed core CTs, iron closed core CTs, have the possibility of having remanence after you're switching off a high DC component. And the problem with the remanence is that the CT are already slightly saturated due to the remanence, and when the next fault coming, then we start from this remanence point and going directly into the saturation. So that means the CT is not carrying the whole fault current, for example. But on the other hand, our algorithm needs a minimum time to detect the external fault detection, or to detect this external fault and say, okay, the differential is blocked due to the external fault. And that's the reason why we considering in the requirements, or in the CT dimensioning, remanence, because remanence can happen. Nobody knows how much remanence we have. you can be a lucky guy, which is going in the opposite direction. So then the CT is carrying the whole fault current. So then everything is fine. But you know Murphy's law. It goes always in the wrong direction. So that means the CT is going directly into saturation. And due to that fact, we considering remanence in the last 2 or 3 years, we got also questions regarding 90% of remanence, and I think there's a good picture to explain that. Yeah, for example, you have a bucket of 10 liters, and you fill up the bucket with 9 liter water, and then you would like to put additional 5 liters in it. The bucket is overfull. So if you're considering the 80%, then your bucket is bigger than 10 liters. Yeah, so that means you have the safety margin that the algorithm is able to detect the external fault and then to block. So, and this is the reason why we say, okay, we're considering in the CT dimensioning already 80%. If it is a bit higher, then we have also some recommendations in our CT in our CT dimensioning, and that's the case. But to be honest, for new applications or for new installations, we always recommend PR cores. That means anti-remanence cores. Or we say, okay, we have to use here linear cores, for example, because those CT cores don't have the problem with the remanence so far.
Okay, so the next 2 questions are about the PX class. So first one is, can you explain a little bit about the PX class?
Yeah, the PX class is it's no big difference between the P class. So the PX is coming from the British standard. So that means here we have specified the knee point voltage, and for that the calculation is a bit different, but the behavior is more or less similar. So for the normal P class, usually we have this PX class in all these countries, which is influenced by the British guys. So and of course, you can use also PX class. You have to specify the knee point voltage. That's the point where the CT is going. Where the CT is going into saturation.
Okay, and last question under the headline CT requirements is, when should be PX class used instead of 5P20?
There is no difference. It's a kind of philosophy in the end. In the end, it doesn't matter if it is a PX core or it's a P class. So in the end, we specified the ALF factor. That means the accuracy limiting factor is specified in our manual. We say, okay, this must be a minimum. For example, for differential protection, we have I think 25 for the ALF factor, means 5P25, for example. Usually for the new dimensioning, usually we have a very small apparent power. Then usually for newer implementation, we have 5P50, 5P60 with 5 AVR for 5 voltage amperes, for example.
Okay. The next topic, questions, I brought some questions with, is the 87N, the restricted ground fault protection. Here, the first question is restricted earth fault protection high impedance versus low impedance. Which is best?
I think that's a kind of philosophy. So in some countries, they like really high impedance fault detection or high impedance restricted fault. But to be honest, I think low impedance is much more easier to develop or to use because you do not need to calculate the resistor, you do not need to calculate the varistor, for example. Therefore, I think low impedance restricted fault protection offers much more advantages also in terms of the CT requirements.
Understand. Next question is the principle of restricted earth fault protection for transformers. Can you maybe explain it a little bit in 1-2 sentences?
The restricted off-fault transformer, restricted off-fault protection for transformer is covering all the cases which we have faced the ground fault close to the neutral point of a transformer, with a very high sensitivity. And it depends a bit on the implementation. We are using, beside the discrimination between the 3I0 and the measured neutral point current, also we are using the angle criteria, for example. So that means we make a discrimination between external and internal faults, which makes the function more robust against CT saturation. So, and of course, the ref protection is especially in solid earth networks and resistive earth networks recommended to detect sensitive earth faults close to the neutral point. And this is also a good add to the differential protection. So that means if you combine both, you will definitely protect your transformer better.
Okay, so they contradict each other.
Yeah, right.
Here also the hint, if you're interested in this whole topic, restricted earthfall protection, our colleague Klaus Wagner have a dedicated session for that in this second series about transformer differential protection. Okay, another question. What is the best way of testing the REF protection, especially considering polarity mismatch with the measured EN and calculated 3I0?
Oh, yeah, that's always the question in the field. And I think you will find out the truth when you have the first external fault and the restricted off-fault is tripping, then you know the polarity of the neutral point transformer was not okay. The question or how to test this, you can test this primary, of course, by injecting primary currents in the system and check the polarity. I think this is one of the best way because there is no chance to have a dedicated wiring for testing and put it through the CT. So the other way is, of course, to checking the cabling, the cable paths, to check where the different terminals is connected in direction to the protected object or in the opposite direction. So that means to the neutral point. This is the other way to do it visually. Finally, the truth you will definitely find out during the first external fault.
Okay, maybe some small things to add. We have also application note about restricted earthfall protection, where we offer also like an Excel sheet, which should help you at least get a feeling about how the function calculates a differential and its restraint current. And yeah, maybe this helps you also when testing the function. Okay. And these are all the questions I brought with me from the last 4 sessions. So if I check the time now, I think we have around about 10 minutes left.
Yeah, right.
So we can go to some of the live questions that came in today from this session 5. Let's jump right in. I read here the first one from a listener called KL. Shall CWA and harmonic blocking be enabled at the same time, or only one of them is enough?
At the same time, it's my recommendation to use both, because both methods are working in parallel. And I would recommend it to use both, because not in all the cases CWA is working, and not in all the other cases sometimes second harmonic is working. Especially in the last years, we saw that most of the new transformers are not producing so much second harmonic anymore. The reason is different, but one of the main reasons, for example, is noise reduction. And due to noise reduction, also the material, the iron is changed a bit, and this new type of iron of metal is not producing so much second harmonic anymore.
Okay.
So that's the reason why we have a second method, and both methods are working in parallel. Yeah.
Okay. Okay. Next question that I read here, I think we already more or less answered. Could you please also give information for the best execution method of restricted earth fault protection? I think here we don't have more to say, right? Let's jump to the next one. How can I access the Omicron Relay Sim test? Is it available freely? Maybe I take this one because the session 5 was my session. Here, unfortunately, it's not for free, as always. Here, please get into contact with the Omicron sales colleagues and to buy a license for that. Also, next question, I think we have to send you to the Omicron people. Could you please show step-by-step how to create a test with Relay Sim test? I mean, not already prepared. Yeah, so this would also be a question more, yeah, that you need to ask the Omicron guys and not us. So next one, which are the parameters to set to take into account the zero sequence current compensation? Maybe that's again for you.
It's again for me. Okay, for zero sequence compensation or for the matrix which is responsible to compensate the zero sequence current, you have to set the parameter from isolated to grounded. So that means we have to say in the settings for differential protection on the transformer side, this side is grounded or this side is isolated. And with this setting, we switch over from not considering to considering or to compensate the zero sequence current internally.
Okay, next question. How the differential relay tripped during inrush with fault scenario? Fault after inrush. What is not blocked by CWA or harmonic blocking? I would say here you already explained a little bit that this is a specialty of the CWA internal fault, exactly to detect such kind of faults.
So that means that the phase which is affected by the fault will not having these usual flat areas. So that means we will see a clear sinusoidal, and this is detected then by the CWA method and said, okay, here we have an internal fault now, and we have to block the second harmonic.
Okay, next one. If in the line there is a PV system, can we set a time delay to the relay in order to apply a fault right through and to control the trip of the relay?
Okay, yeah. This question is not easy to answer. So the question is if the PV system is in the protective zone or not. If it is outside, of course, we usually have to detect this as an external fault, and we have the external fault blocking for it. There's an external fault detection and external fault cross block. And this setting is usually set to 300 milliseconds. These 300 milliseconds comes from the external fault clearing time. So, and usually the differential protection is done in this case not tripping, because for the differential area, it's an external fault, and then the fault needs to be clear by the network fault protection, for example.
Understand. Okay, the next one, Omicron and digital twin. Is it for consultants or installers or EPCs? So here I would say this is for everyone who needs to test relays, especially our Sipotec Twin is also for when you make a parametrization and want to check if the device is running.
That's good. Yeah, I would say for all the different roles, which is working with electrical protection. Yeah. It starts with the engineers. It starts with testing, commissioning. Also with training purpose, for example. We are using it very often for analyzers, for fault analyzers. For example, if you want to figure out if the polarity of a CT was switched, you can translate the existing record and can change the settings and find out, okay, now the protection is stable. So that means for everyone with the different models or with the different roles inside the company can use Omicron and digital twin for testing. Yeah.
Mm-hmm. Okay, next question. How does the CIPROTEC 5 system meet cybersecurity compliance standards required by utilities worldwide?
Yeah, cybersecurity especially it's a platform feature, so that means we are taking care on all the cybersecurity standards and regulations. So that means we are currently, or we are continuously develop new cybersecurity feature in our system to be compliant with all the standards and the customer requirements and so on. And this is I think a very good topic for especially for such a platform like CIPROTEC 5. So that means we not having cybersecurity in one of the different devices. So that means it's a platform idea. So that means we have implemented it over the whole platform. We have also implemented cybersecurity requirements for all the different elements in our portfolio.
Okay. I think we also have dedicated cybersecurity webinars.
Yeah, of course.
Okay. All right, next question, a long one. As the Siemens CIPROTEC 7 UT8 supports multiple protection functions such as transformer differential, distance, line, current differential, and busbar protection, is Siemens shifting towards a universal protection relay concept instead of dedicated relays for each application? Not with the 7UT, I would say.
Okay, we can say the 7UT was the first universal device because I saw that the 7UT is on a electrical equipment installed, which has a lot of boundaries to other protection systems. So that means on one hand we have the differential protection, on the other hand for transformer on the other hand we have, for example, distance protection, line differential protection, and so on and so on. That means we will definitely have the dedicated devices, the type devices for the future, because not everyone would like to use a universal approach. That means beside the dedicated devices, the type devices, we will have also the concept with the universal devices. I think these are different kind of users which is looking for these kind of universal devices, but to be honest, we will have both in parallel.
Okay. Okay, I would say 2 more questions roundabout. Can the 7UT8X be used as overall differential with 1 GSU, 3 UATs, and 1 generator? What is GSU?
Step-up transformer, I think. Yeah. Okay. Of course, you can use the 7UT87, for example, for that application with 3 times differential protection. That means to cover the overall protection from the high voltage side to the neutral point of the generator, and covering the auxiliary transformer and so on. Then you can have a dedicated protection for the step-up transformer, and as well in the same device you can have also a dedicated protection, differential protection for the auxiliary transformers. So, and this is possible with the 7UT87, which offers 3 times differential protection in parallel in one device. Yeah.
Okay. As a last question, I picked the one about the RAF protection. Does the X to R ratio make a difference in choosing high impedance or low impedance REF protection?
I don't think so. I don't think so.
Okay, short answer. Then I would say we close the session now. And yeah, thank you very much for all the questions, for all your attention. We are now finished with this first series consisting of 5 sessions in total. As already mentioned before, we have a second webinar series about transformer protection from our colleague Klaus Wagner. And yeah, from my side, thank you and have a nice day.
Thank you very much.
Goodbye.